First, I want to make an announcement. This week, the usual office hour, I will not come to the usual office hour on Thursday, but instead we'll have an office hour from 12:30 to 2:30, and it will be not me doing the TA music. So, it's office hour. Thursday. So it's also in different room. It's only this week. Okay. So now about what we are going to do today. Last time we talked about quadratic reciprocity. We talked a lot about how to take a Einstein equation and reduce it modulo a prime number, try to solve it modulo this prime number. And we talked a lot about when can you extract roots modulo a prime number, when you can divide modulo a prime number. So we developed quite a bit of theory modulo a prime number. And today I want to discuss things which are not really of this flavor. It's not about something modulo a prime, it's really something about integers. And what I actually want to discuss is the following thing. Sometimes we want to solve an equation in integers, but in between the initial formulation of the problem in the integers and before the final answer, which is also in integers, we work with some other things. For example, when we try to parameterize invariant triples, it was convenient for us to work not with integer numbers, but rather with complex numbers, with rational numbers. And in rational numbers, we could divide, we could talk about line passing through 2 points with rational coordinates and so on and so on. So we had some additional freedom. And this freedom allowed us to apply some additional reasonings. So today I want to talk about kind of the same thing, but in different contexts. So first thing, let's old-fashioned equation. 1 is x squared minus 4y squared. It's a very simple equation, so maybe somebody has an idea what to do.
So this is x minus 2y.
Yes, that's factor. X minus 2y times x plus 2y is equal to 1. We know, so I want the solutions in integers. I know that the product of two integers is equal to 1. Well, there aren't that many integers whose product is equal to 1. Basically 1 times 1 and another one minus 1 times minus 1. So I have x minus 2y and x plus 2y should be either plus 1 or minus 1. Both of them. And then I know that x is plus or minus 1, y is equal to 0. Just solve this linear system of equations. So it's a very simple equation, and what made it simple is that the fact that we can actually factor this thing as a product of two factors. Let's try a more complicated one. So, actual question, So, such an equation is x squared minus 2y squared is equal to 1. Okay, so you found the solution to plus minus 3, plus minus 2. Okay, here's one solution. Let's even see another solution. Oh, there is an obvious one. So this one. So can I write this one as well? But it's not the only one. If you try well, how can we try to find solutions, a couple of solutions? Well, if y is equal, well, always you can assume that y is a positive. If it's negative, you can switch the sign and get positive y without changing the x. So we try y is equal to 0, we get x equal to 1. Y equal to 1, we get x squared is equal to 3, no solution. Y equal to 2, we get this solution, x equal to 3. Y equal to 3, 4, 5, it doesn't work, doesn't work. And then the next thing, well, the next solution that we will find is like this. X equal to 17, y equal to 12. Once again, plus minus, plus minus. But once again, even this is not the last solution. In fact, there are many more. We'll see that there are in fact infinitely many solutions. So the question is how to find all of them. And well, one idea is, let's look at what we did here. We factored this form as a product of two factors. Well, here I can also factor it, but not in integers, definitely not in integers. In real numbers, I can factor it. So in real numbers, I have such a thing. X minus square root of 2y times x plus square root of 2y is equal to 1. Well, that's interesting, of course, but, well, I can't take the next step. Here, the next step was 1 is a product of two integers, hence we know the integers. Here it's much more complicated. 1 is a product of two numbers which are really not integers, where integer plus or minus square root of 2 times another integer. And complicated now. So it's not that obvious what to do here. But here's a funny observation. Suppose I have two solutions to this equation. Say I have observation. Suppose we have two solutions of this equation. xy and x prime y prime. So I know that x plus square root of 2y times x minus square root of 2y is equal to 1. And suppose I know another solution. Let me multiply these two equations one by the other. Multiply them. What do we get? Well, it's this times this times this times this is equal to 1. Let me write it down. X plus square root of 2y times x prime plus square root of 2y prime times x minus square root of 2y x prime minus square root of 2y prime is equal to 1. It looks like this equation is kind of different from these equations. But look, if I combine these terms like this, I combine this with this, and I combine the last two terms like this, and open the brackets. So let me do this. I open the brackets here, and I get f x prime plus 2 times y prime plus square root of 2 times x y prime plus y x prime. So I get this factor times, well, what is the other factor? It should, in the other factor, everywhere I just replace square root of 2 by minus square root of 2. I mean, this is just the same as this. Is square root of 2 replaced by minus square root of 2. Same here. So to get the other factor, I can just look at this one and replace everywhere square root of 2 by minus square root of 2. Or alternatively, I can just open the brackets. So I get basically the same thing, plus 2 y prime, but with minus square root of 2 x y prime plus y x prime. equation looks exactly like that one, but for different numbers. It is of the form something plus square root of 2 times something else times the same thing but with minus square root of 2 is equal to 1. It's exactly this equation. So we get another solution. We get x tilde y tilde. Let me rewrite those things. So it's x tilde plus 2y tilde. Sorry, x prime plus 2y prime. And y is equal to x y prime plus y x prime is another solution. If I have two solutions of this equation, I get another solution. Well, did I have to factor? What is this magic? How does it work? Well, somehow we can actually verify. So, i.e., what it means is if you know that x squared minus 2y squared is equal to 1, and the same about x prime and y prime, then, well, we have funny identity. X prime plus 2y prime squared minus 2 times x prime plus y x prime squared is equal to 1. So that's what it means. It's kind of funny identity. If you know this and this, then automatically we have this. So if you are bored now or something like this, you can try to see directly why it follows. But we already proved it using some factorization, using square root of 2. So let's see an example. Let me start with one of the solutions. Say, let me take xy to be equal to 3 and 2. And let me take x prime y prime to be the same solution. Well, I have two solutions. I can sort of multiply them in this way and get another solution. X tilde y tilde, like this. It's this x prime, so it's 3 times 3 plus 2 times y prime. And y coordinate is xy prime, so it's 3 times 2 plus 2 times 3. So we get the solution 9 plus 8, 17, 12. So directly from a solution which was very easy to find, somebody actually did find it, we got a solution which is much harder to find. Well, we can continue this process. We can take this solution, this new solution, and multiply it by, say, 3, 2. So we can take more generally, we can take this solution and multiply it by itself as many times as we wish and get a whole bunch of solutions, infinitely many solutions. Actually, infinitely many solutions. So the way to find infinitely many solutions is like this. The way to find infinitely many solutions. Well, take this number, 3 plus square root of 2 times 2. That's the thing that we start with here. Multiplied by itself n times. We know that it should be written in some way as x plus 2 square root of 2y. So it's equal to x plus square root of 2y. Once you write it in this way, x and y are integers, some positive integers, well, they have a solution. So xy is a solution. So how to see this? Well, take this number, multiply it by the same number with square root of 2 replaced by minus square root of 2. So, the observation why this is true. Proof. Explanation. What is x squared and 2 times y squared in this case is x plus square root of 2y x minus square root of 2y. The first thing in the product is, well, it's given to us, it's 3 plus 2 square roots of 2 to the power n. The other thing is the same thing, but the square root of 2 replaced by minus square root of 2 everywhere. So it's just 3 minus square root of 2 times 2 raised to the power 2. Well, now let's use the fact that we can actually multiply these powers like this. It's 3 squared minus 2 times 2 squared to the power n. And this we can just compute. It's 9 minus 8, which is 1. So you see, we've got a huge sequence of solutions. Well, maybe let me ask you a simple question. Why are they distinct? So we got for every n, for every say integer, positive integer n, we got a solution. Why are they all distinct?
Because each power of that number is strictly greater than the previous power.
Yes, exactly. So this number is, well, it's an actual real number. It's not only a recipe to produce x and y, it's actual number. We can take this number, it's some number which is, well, greater than 5 even. So if you take distinct powers of this number, you get distinct answers. Yes, it is true, you can write each answer as x plus square root of 2y in some way, so you get distinct solutions in this way. Yes.
I was thinking, we already have a way to find the infinite by drawing a line through already known solution.
So,
Like, are they the same or which one is better?
so actually, if we are trying to solve this equation in rational numbers, then you're right. So in rational numbers,
Oh, in rational.
yes, you're absolutely right, and it's a very good point. So in rational numbers, this is an equation of hyperbola like this.
Okay.
And if you want to solve it in rational numbers, yes, indeed, you can take one of the solutions, say 0, 1. So it's probably like this. One, 0. Take this solution, join it to any other solution which has rational coordinates.
Yeah.
By line, this line will have a rational slope, and the slope parameterizes everything.
Yeah.
But if you want this point to be integer,
Okay.
well, it doesn't mean that the slope is integer.
Sure. Okay.
The line will have two intersections.
Sorry?
The line just to do it.
Yes.
Will have two intersections. I mean, the other intersect the other branches.
Oh no, it doesn't intersect the other branches. Quadratic equation, it intersects the line, it's exactly the place.
Oh.
But the problem is, even if you have two integer solutions, the line that passes through these two integer solutions, well, doesn't have to have any integer slope. Nothing that's special about the slope. So, okay, you're right. You do know how to solve this question in rationals, but now the question is which of the rational solutions are integers.
Okay.
And that's really not that obvious. Yes. Okay, so you got infinitely many solutions, they're all distinct. The natural question is if you find all the solutions. Well, let's see. I claim that yes, we didn't define all the solutions, and we actually don't really need any other tricks. This trick with factorization actually is useful enough to prove that we found all the solutions. So let me formulate a theorem. Any solution positive x and y. Is of the form x plus square root of 2y is equal to 3 plus 2 square root of 2 to the power n to some n. The idea of how to prove this theorem is like this. We have, well, it basically still uses the same idea of taking a solution, x comma y, and producing from it a different solution. And we have to produce a solution which is much smaller than the one that we started with. Actually, we'll find a solution which is smaller than this solution, 3 plus 2 times square root of 2. So that's the idea. Proof. We'll start like this. Let's take a solution. So let xy be a solution. Find n such that we take this x plus square root of 2 times y with some number, some. So maybe I should say first, then x is at least 1. That's obvious. If you have x squared minus 2 times y squared is equal to 1, then x squared is at least 1. So x is at least 1. So now find n such that if you take this number x plus square root of 2y and divide it by power of this number, 3 plus 2 times square root of 2, so we can take such number n so that this number is still greater than 1. I mean, I will keep dividing by this number, 3 plus 2 times square root of 2 is a number of something 5 or 6, so let me keep dividing by this number until I get a number which is still larger than 1, but I cannot divide any further. So I will get into the interval between 1 and this number, 3 plus 2 times square root of 2. If at some point I am still outside of this interval, I can keep dividing and not get out of this interval at this age. Once I fall inside of this interval, well, I stop. So here are the claims. I found this number, first claim. It is of the kind something plus square root of 2 times something with integer coordinates. So first claim is like this. This number x plus square root of 2y divided by 3 plus square root of 2 plus 2 times square root of 2 to the power n is of the form x prime plus square root of 2y prime with x prime, y prime integers. Not only this, the integers and the solutions of the original equation. X prime squared minus 2y prime squared is equal to 1. Does anyone see why? So, to be honest, I proved the following thing. If I have x and y solution of this equation, and I take one solution multiplied by another solution in this way, x plus square root of 2y times the other thing, I get something from which I can produce, well, which corresponds to a solution. here I'm doing something else. I'm taking x comma y and divided by 3 comma 2 to some power. So I'm taking the quotient. But here's the funny thing. What is 1 divided by 3 plus 2 times square root of 2? Well, actually, we know that 3 plus 2 times square root of 2 is a solution of such equation. And 3 minus 2 times square root of 2 is equal to 1. So this number, 1 over this, is actually such a thing. 3 minus 2 times square root of 2. Just, well, because 3 comma 2 is a solution of the original equation. So if you take, well, this thing, x plus square root of 2y divided by 3 plus 2 square root of 2 to the power n, you get the same thing as if we did the following. X plus square root of 2y times 3 minus 2 square root of 2 to the power n. Just the same thing. And now it's obvious. If this is equal to x prime plus square root of 2y prime, well, first of all, it's obvious that it can be written in this way with x prime and y prime, which are integers. Just open the brackets. And also, it's obvious that x prime and y prime are solutions of this equation. X prime squared minus 2y prime squared is equal to 1. Because of this observation, if you take two solutions and multiply them, you get another solution. X prime plus square root of 2y prime times x prime minus square root of 2y prime is 1. Because here we have these times the same thing with minus sign is equal to 1, and here we also have the same thing. So we got a solution, x prime y prime, integer solution to this equation, and what else can I say about it? It's a solution which is between 1 and 3 plus 2 square root of 2. Well, still, it seems that it's possible that maybe y prime is negative. I mean, I would want to claim that it means that both x prime and y prime are somehow small. But for now, there is still an option that I started with a large x prime, subtracted some large multiple of square root of 2, and landed in this small interval. Well, no, not true. I claim that both x prime and y prime are positive numbers. Does anyone see why?
Well, then you just argue from here.
From here,
The previous one.
previous time, okay?
Because if y is negative, y prime is negative,
Yes.
we simply have a minus sign with this positive counterpart.
But you know, here we do have a minus sign. So when we open the brackets, it seems that it is possible to get a negative answer. But you know also that x prime and y prime are solutions of this equation. So look here. This number is greater than 1. So this number is smaller than 1. But what is, so let me do it like this. I know that x prime plus square root of 2y prime is definitely greater than 1. That's by construction. And I know that the product of this and x prime minus 2 square root of 2y prime square root of 2y prime is equal to 1. Hence, x prime minus square root of 2y prime is smaller than 1. But then what is y prime? Its smallest the difference of this and this, well, not exactly, it's 2 times square root of 2 times y prime is the difference. So 2 times square root of 2 times y prime is the difference. And it is positive. Well, so this is positive, and x prime is also positive, just because it is half of the sum. So 2x prime is the same thing, even simpler, plus the thing is also positive. So x prime, y prime are positive numbers, they are solutions of this equation, but they are also not very large, because x prime plus square root of 2 times y prime is, I already erased it. Let me collect all the knowledge that we know. X prime plus square root of 2 y prime is smaller than 3 plus 2 square root of 2. X prime and y prime are positive, they are integers, and so they are a solution of this equation. Well, there aren't that many options. I mean, x prime can be, well, if y prime is positive, so x prime should be at most, say, 5, 6, something like this. Y prime can be at most something like 3. So, just not that many options. We can check all of them by chance. So, the only possibility is x prime by prime is equal to 1, 0. So the quotient of the solution that we started with, so hence x plus square root of 2y divided by 3 plus 2 square root of 2 to the power n is equal to 1, is equal to x prime plus square root of 2y prime, which is 1. So this number is equal to the power of this solution. Hence, x plus square root of 2y is 3 plus 2 square root of 2 to the power n. So the logic of the proof is once again like this. We have, well, first of all, we identify solutions of this equation, x squared minus 2y squared is equal to 1. Instead of these solutions, we look at such numbers. X plus square root of 2y with the property that once you multiply this number by the same thing with square root of 2 replaced by minus square root of 2, you get 1. Once it's written in this form, it's obvious that if you have two solutions, you can multiply them and get another solution. It's almost obvious that if you have two solutions and you divide one by the other, you also get a solution. Just because if you have x plus square root of 2y, then 1 over it is x minus square root of 2y, which is another solution. So 1 over a solution is another solution. Same thing, but with minus sign in front of y. And now take any solution, multiply it by large enough power of the smallest solution you can find, you will get a solution which is small enough so that we can actually find out what it is. So now take any number, any solution, x plus square root of 2y, divided by some small solution, 3 plus 2 square root of 2 to the power n, divide by enough powers of this small solution so that you'll get a solution which is very small. Once you have a very small solution, well, you basically have just find many options to check. A solution, a small solution. We'll prove that it is trivial solution, 1, 0. That's the outline of the problem. So basically, I mean, conceptually at least it's very simple. Maybe there are some small technical details, like why in this solution we have positive coordinates, why such small things, but conceptually it's very simple, but only after you introduce this idea of extracting square root of 2. Yes, the problem is about integers. Yes, you can even write down the answer as in integers. I mean, for now we got an answer that involves square root of 2, but we can rewrite it. So let me rewrite this answer. How can I actually find x and y? Suppose so answer will be written. If I know that x plus square root of 2y is equal to 3 plus 2 square root of 2 to the power n, I know that x minus square root of 2y is the same thing, but with square root of 2 replaced with minus square root of 2. And to find, say, x, I can do the following. I can just take the sum of these two things. So x is 1/2 of the sum. 3 plus 2 square roots of 2 to the power n plus 3 minus 2 square roots of 2 to the power n. And, well, if you know the binomial formula or something like this, you can open the brackets and get a formula that doesn't involve any square roots of 2. So something like this will be sum. Well, I will probably get the wrong formula, but something like this. N choose k, 3 to the power n minus. So 2k, 3k, and 2 square roots of 2 to the power k. So 4k to the power k. And probably minus 1 to the power k. Something of this form. I'm not sure, but you can open the brackets and get a formula that doesn't involve any square roots of 2. So once again, I'm not sure that that's the correct formula, but something of this form should be true.
I think if you just get rid of the negative 1 to the power k, it should be fine because the negatives all cancel out.
Yes.
And the even powers are positive.
Yes. So I think it's like this. Yes. Yes, all the negatives cancel out. We have only positive terms, and we have only even terms which contribute because, I mean, only even powers of 2 and square root of 2, so we don't have any square roots of 2 in the answer.
You can have 8 that you can.
Yes, 8 is
right.
square root of 2 squared. Well, so we got, in the problem about integers, we got a solution which, yes, can be written in terms of integers, maybe not a simple formula, but can be written in terms of integers. But to be honest, to find this formula, find this answer, you actually have to go through adding the square root of 2. I mean, yes, you can try to formulate anything without it, but it's really not nature. So to go from the original problem to the solution, you have to go in between through the world of, well, the world where square root of 2 actually exists, not only integers. So if you live in ancient Greece and you don't know that square root of 2 is an actual number, well, it will be a problem when you try to solve this equation. Okay, so maybe any questions about this equation? Actually, this equation is part of family, well, larger family of what they call pair equations, and well, maybe I will formulate a theorem about them, but we won't go deep into the theory. So, theorem D is 3, which means it's not divisible by square of any number. So square divided by 3 implies that n is equal to 1. squared minus square root of d, oh sorry, minus d times y squared is equal to 1. It's called Bell's equation. So its theory is, well, basically we solve the case when d is equal to 2. The general theory is kind of close to the case that we solved. With a small difference, it's not obvious how to find one non-trivial solution. We found the solution 3, 2 to our equation. Here it's not obvious what solution to take. But if that's not, why not, is the smallest solution, oh, is the solution with the smallest x naught plus square root of d times y naught, which is greater than 1, so strictly greater than 1. So there is always one very trivial solution, 1, 0, but it doesn't count. We want the next largest solution, so we find the next largest solution. Once you found the next largest solution, then if this is the second smallest solution, then every solution is of the form x plus square root of dy is some value of the given solution. Plus or minus. If I want to allow positive and negative x and y coordinates. So in fact, more or less every solution is a power of minimum 1. And once again, to solve this equation, you actually have to be working with square root of d, which is not an integer. Okay, so eventually I want to answer the following question. So here I will stop with Bell's equation. I will not go into the theory of how to find the small solution. It's very beautiful, very interesting, but probably not really relevant to our course. What I want to do is the following. We want to discuss eventually such things. What numbers, so new question, what numbers are of the form x squared plus y squared. Some integers x and y. So we already discussed something like this. What squares out the form x squared plus y squared? We solved completely the question, well, of solving this equation. Z squared is x squared plus y squared. That was Pythagorean triples. Now we want to understand more generally what numbers n can be written as sum of two squares. So let me rewrite it for what n. N is equal to x squared plus y squared. And the idea is, well, this thing x squared plus y squared is kind of this form. X squared plus minus some number times y squared. Well, here it's not really minus. Let's make it a minus. N is x squared minus 1 y squared. So I want to solve such an equation. Well, the general tricks that we've seen today is try to factor it and maybe something good will come out of this. Well, so let me rewrite it as x is equal to x minus square root of minus 1 times y, x plus square root of minus 1 times y. Well, we got some kind of expression, but once again, if you live in ancient Greece, it doesn't make any sense at all. Not only are we extracting square root of some number such that the square root of it is not a rational number, it's not even square root of 2, we are extracting square root of negative number, square root of negative 1. And we learned in high school, if you take a number, multiply it by itself, you always get a positive number. Well, not negative number. But here we get square root of minus 1. On the other hand, well, maybe we don't really care about the meaning of square root of minus 1. All of the manipulations here, well, we could have explained them to ancient Greeks who didn't know what is square root of 2. I mean, I only did algebraic manipulation with this symbol, square root of 2. I didn't tell you that it's exactly 1.41 and computed infinitely many more digits. No, I didn't. I just told you it's some number whose square root is equal to 2. That's the only thing that I used in all my computations. So maybe here we will be able to develop some theory, and we won't have ever to explain what is actually a square root of minus 1. Oh yes, it turns out that in this case we can do this, and in this case it's an extremely useful trick. We'll see how this theory develops. In general, it is a very useful trick in mathematics to pretend that square root of minus 1 is an actual number. And so I hope that some of you, well, most of you, have seen this trick in other contexts. I will start the next hour by repeating some of the basic arithmetic. So what happens if we pretend that square root of negative 1 is a number? And then we'll start developing this theory of what can give us a number here. So let's have 10 minutes here.